you, the organizers, for the opportunity. And I will be speaking about vortices, but in another system. It's not superconductor, it's in superfluid and in droplets of superfluid. That is the case of Bose-Einstein condensates, kept in traps, in magnetic traps, where we can introduce vortices and keep putting energy. Those vortices go evolve, produce a tangle configuration, and then the evolution is typical of turbulence. And because it's in a superfluid, it's called quantum turbulence. The idea comes from Feynman, right? And it's being a field that's being explored in liquid helium. And now recently, we demonstrate that it's possible to do in Bose-Einstein condensates with some advantages, I think, because we can have a mixture of superfluids, we can control interaction, we can do everything that's interesting from the point of view of understanding a little better turbulence. And I will present to you mostly experimental work, but of course we have a lot of partners doing theory, so I will present some of the theory that people are doing. Okay, well, this is my group, or our group in São Carlos. Is a big number of people, and I would like to invite you to everything we do is in our homepage, and I'm not going to put all the references during the talk, but here we have a complete list of publications on what I'm going to tell you here today. And we are a center, and we do atomic physics, biophotonics, and nano. So we are 7 faculty people together in the center. And basically what I'm going to tell is all related to atomic physics, right? And this is the subgroup doing Bose condensates. And we have good collaborators from outside. I would like to stretch the collaboration with Yukalov from Dubina, which is from the Bogolyubov Institute, he does a lot of the theory for us, things related to the dynamics of the evolution of the turbulence. Carlo Barenghi from Newcastle, also a theoretician. Makoto Tsubota from Japan, from Osaka City University. Alex Fetter, that most of you know. Andy Hewlett, Robin Kaiser, Jaco Roati. They're all collaborators, mostly in theory, because this is a field that we need all the support. Well, you all know about turbulence. You know it's a challenge. It's listed as a challenge. We still do not know a lot about turbulence. It's an old field, but still not well understood. And why people care about turbulence in superfluids? Well, because interesting system. But more than that, it's because we believe that we can understand some aspects of turbulence in a less complicated fluid than the normal classical fluid. First of all, here all the vortex lines are equal, are quantized, so it's better to deal with. System normally can be smaller. You can have a tank of liquid helium, but you can have a 10 to the 6 atoms in a condensate that can do the same. And people believe that it's simpler to understand a few of the cascade phenomena that takes place in turbulence. So that's why we are excited about turbulence in quantum fluids. You may not know, but turbulence is everywhere. You could not exist without turbulence, right? So if turbulence was not in your body, the flow of blood could not exchange nutrients with the walls, because laminar flow has a zero velocity flow at the walls. You could not breathe. Your lungs could not efficiently exchange oxygen if it was not turbulence. Your brain could not also oxygenize it well if it was not turbulence. Anyway, you could not exist if it was not turbulence. And people claim that if it was not turbulence, we'll be all dead anyway, because the amount of pollutants in the atmosphere is mixed and spread by turbulence and everything. So you see, it's a very important field. And in quantum fluids, which is this topic, people realize that since you can make quantized vortices, And those vortices can react in those crossing type of phenomena. And then they create oscillations on the vortex line, and these keep crossing, producing rings and many things. So you can evolve to a turbulence in the quantum fluid, even though you don't have dissipation. And it is a very specific, a very special fluid. We all know that you have turbulence. You need to have randomness. You need to have dissipation. You need to have scaling. So things has to be invariant for some scaling in velocity and time. And you need a cascade. Energy has to flow from large to small scales. And here we somehow combine everything. You may be thinking, where is the dissipation? Those reconnections of vortex lines take to atomic scale, where you can dissipate like sound waves in the system. So people already figure out to fulfill the requirements of having turbulence, even though this is a irrotational fluid and dissipation less. Okay. Normally studies are done in helium. We shake objects inside the tank of helium, produce vortices, put another set of wires that also detect the motion, all this thing, and try to understand. And this is being done for a lot of people. And now comes the condensates. You know, condensates, I'm gonna explain this. I think this audience knows very well all the things related to vortices, right? So I'm not gonna discuss this, but except that here, this is the Healing length. And the Healing length is a function of density and scattering length. So in fluids, this is the size of the vortex, right? And the equation that solved this is the Gross-Pitaevskii equation. And Gross and Pitaevskii got famous for proposing a mean field equation that are able to reproduce the vortex. And once you make vortex, you make lattice. Exactly like a Brikosov type of lattice, because vortices here also interact. And they are confined in the fluid, so you crystallize. Okay? And then the idea that we had was to make a big confusion for the vortex, so they start to react very fast and evolve to turbulence. So a characteristic of quantum turbulence is that we introduce energy in large scale. So vortices are big, as you saw. We can see by eye because the density is low, so the Healing length is high, and we can even see the vortices by eyes in a very nice way, and we can study them. So energy is injected in large scale and start to, so you see we have these reactions, reconnections and everything. We have two main mechanisms. We have the Richardson cascade and the Kelvin wave. You know, this is by reconnection of vortex line. This is ring being reconnected and being reacting to a small scale. So energy then flow until there is a sound emission on the fluid. That is something that we know well, is this Kolmogorov energy scaling law that seems to be common for all the turbulence present in classical fluids, and also in some big, large system of superfluid. But in the condensates, that may not be so. And this law, the Kolmogorov law, that is how the energy, the spectrum goes with the momentum, is really produced by making the invariance in scaling, right? And it's well known, and people normally require that a kind of power law of this type be present for you to have the cascade, energy flowing from the scales and characterize the turbulence. And my talk will be mostly measuring the equivalent of Kolmogorov law for the condensate, convince you that we have a very nice system there. I have two experimental systems doing turbulence in São Carlos, and we work with rubidium atoms, so we going to produce almost 1 million atoms in a condensate and try to punch a hole, which is the vortices, and evolve to turbulence. And we have another one that now is starting to run, where we want to mixture two superfluids. This is something we can do, and you cannot. You cannot mix two superconductors, but we can mix two superfluids. And we can transfer vorticity from one to the other by turning on interaction. So this is an extra knob. Or maybe he wants to correct me. You can mix two. Oh, sorry, then. You can. But not in the same position, right? The same position. So, it's all equal. Everything I'm going to say here, we can find in superconductors then. Oh, okay. Well, this is the mixture superfluid. We work with sodium, potassium. And the idea is to have a knob to control turbulence. The dream is produce turbulence in one, start to turn on interaction, and then vorticity will migrate. Eventually, we can control migration of turbulence from one to the other. And then if we can do that, we can understand a lot of the mechanism of turbulence. So this is is in progress, but the things I'm going to discuss to you is mostly related to the first experiment. I'm not going to speak about this now because I see my time is running very fast. And we all believe that doing in BEC is very nice because we can do in many dimensions. We can control and we can reach turbulence with a few vortex lines. System is small, it's finite. We can reach turbulence with 50 vortices instead of millions. So it's a nice system, and there are a couple. I was going to make a parallel of all the things, but unfortunately, we started this business of experiment with turbulence in BC in 2009. Now there are many groups around the world doing, and more are coming. And we go for 3D system, and many people are going to 2D. They are different in some sense, right? But and this is a sequence of work we have done. Everything is blue here is already published, and the ones in red is on the process, and everything is in my site, in the homepage of our group. How we excite vortices? We shake. It's like I call a washing machine, because the idea is to introduce momentaneous rotation in all directions. Tsubota proposed that we should rotate a condensate this way and then that way. So we're going to generate. But this is not so trivial to do in the lab. In the lab, it's much easier to shake. And then you introduce perturbation, enough vortices start to be generated. They accumulate, and they propagate, and they react, and they produce a turbulent cloud. So this is what we do. The whole sequence is here. We produce a BEC. We excite, like this shaking excitation. We hold for some time to wait the things to equilibrate. The idea is to see the decay, but all the papers we have published and the work, we still characterizing what's going on during the excitation. Now we're going to start the decay process. Then we do a time of flight, and we map by absorption. So we do a in-plane momentum projection, because we have a 3D cloud, but we come with a probe laser, and we do absorption. So we project everything. And by the expansion and everything, we determine the momentum distribution. So along the time, we have to show that we have a vortices, anti-vortices, which is essential. So we show that I think we are the first one to demonstrate the tripoles of vortices. This is a vortices of the same sign. So they try to make a triangular type of configuration. And if they are one with the opposite, they try to align. This is much less stable than the other, but even though they exist. So everything we do is more or less summarizing this diagram. We vary the amplitude of excitation, the time of excitation, and we observe what's going on in the system. And this is, first we see this kind of scissor mode, which is related to the superfluidity. Basically, you see a bending mode of the main axis of the drop of the condensate in the trap. Then we generate vortices, and then those vortices start to react, evolve to turbulence. And if you keep pumping energy in the system, this goes to granulation. Granulation is a kind of breaking domains of superfluidity, which if I have time, I'm going to show you some of the study on the granulation. We don't call fragmentation because for BEC, fragmentation means something else. And we call granulation. So how the things start, you start to nucleate vortices. This is real absorption picture. And then suddenly you generate enough. This is a finite size system. They start to react. So the rate of vortice formation change. And then here is when the turbulences start to take place, because here is where the energy you're putting goes mostly to make the vortices to reconnect and produce the cascade. If you wait long enough, the vortice seems to disappear, and something else goes. So we don't have only a vortice type turbulence. We have also, this migrates to wave turbulence and so on. At the end, normally we have a wave turbulence type of system. Okay, well, this is a kind of picture you see. Single vortice, many vortices producing the turbulence, and this is when they have this transition. It's not really a transition, it's more like a change to a granulation type of state. A few things we observe in the macroscopic view of the condensate. One of them is the way that these expand. As you know, a classical fluid in expansion does not matter the shape, always goes isotropically, right? Because you have Maxwell-Boltzmann distribution for the momentum anyway. If you have a pure Bose condensate, you have an inversion of aspect ratio. So whatever is more squeezed, expand faster. So this is the Bose condensate. And when you have a turbulent BEC, none of those happens. It goes in a self-similar expansion. This was explained by Fetter, Monica, and Gordon Bain in a paper showing that random distribution of angular momentum actually cause the cloud to expand in a self-similar way. And we have a good explanation for that. And then comes the spectrum. We have to find how is the momentum occupation. By the way, a normal condensate is interaction dominated. Kinetic energy we throw away. When we go to turbulence, we invert. This is a kinetic dominate state. All the energy is mostly kinetic, okay? And we can obtain the spectrum, which is the most relevant thing here is to make comparison. And there is a range of momentum that's called inertial range, where the energy does not dissipate but flows from the scales. And this is when the Kolmogorov law starts to be valid. And this is what we're measuring. How you measure the momentum distribution? We just let expand. And whatever the atoms with less momentum will fly less. The atoms with higher momentum will fly further. And then by mapping this, because it's a kinetic dominate state, by mapping how much atoms reach different situation in a time of flight, and then we do a Abel transformation, we can recover the momentum distribution. Okay, so this is the way we do the measurement. And what you obtain, if you have a few vortices, you have that not so excited spectrum. Instead of speaking about energy, I will be speaking about momentum occupation, which the integral of the momentum occupation will provide the energy spectrum, okay? So, but whatever you establish the turbulence, the atoms migrate to the higher momentum and some power laws start to be evident in exactly the correct range. And this is what we've been studying, but it's not minus 5/3, it's -3, the power law type of behavior. And we see the migration, so we see the cascade taking place, the atoms migrating to higher momentum occupation. And we've been studying this. And then as you vary the excitation time or amplitude, you can fit on the inertial range what is the power law. And we see that the power law goes and then established when the turbulence is established and the cascade starts. Because up to this moment, the things is evolving is not a fully developed turbulence. But in the moment that is fully developed, cascades start to take place. And then the power law is really established. Okay? But it's not that number that everybody claims that should be the -5/3, which is the Kolmogorov law. It's very different. And the reason that's different, we start to understand. This is a full diagram showing everything, and I put this because just looking to the power law dependence, we can recover the diagram. Depending on whatever exists or not, the cascade, we can map. And there is here some of the systems that the momentum, I show you a plot, this plot. But suddenly, if I keep putting energy, this is going to start to go up again. And this is not well explained yet. So somehow the system starts to recover and comes back to probably going to try to recover. And probably all the energy is already going somewhere. And the system starts to recover, not being turbulent here. Okay, so just for you to have a taste of how I'm exciting here. And then suddenly, the turbulence starts to establish. So this is a picture of the absorption. We do correlations, second order correlation, density-density correlation, and we apply the concept of power spectrum to recover the energy. So we do measurement in two ways: momentum, directly momentum occupation, or second order correlation, density-density correlation, and from there, from the Fourier transform of the correlation, we obtain the power spectrum, and then this is already the energy spectrum, and everything seems to match well both measurements, either with the momentum or directly with the power spectrum that's related to the energy of the system. Well, we've been studying how the things evolve, the energy and everything, and it seems to be compatible to a final stage of wave turbulence in this system, and now we're studying the evolution of this. Now, sometimes we want to characterize the order, the disorder of the system. So we use this concept of the differential entropy, which is basically the integration of the density and logarithm of the density. And of course, when the turbulence is established, here things are happens, but here is when the turbulence is established, and then the entropy starts to grow, or this entropy. It's very interesting because this entropy evolves even if you take out the excitation. So if I take out the excitation, this is the holding time. The disorder still taking place. As the reconnection moves and goes, this grows. Well, recently a paper by Yukalov shows that actually the system is more complicated than it seems. We go from the equilibrate condensate, and there are many, many stages from which we pass, and we are now trying to characterize all those stages until we reach the final stage, which is the wave turbulence. And to do that, effective temperature is being defined, and instead of, we cannot use a Reynolds number here, but we can use a Fresnel number with something related to optics. Remember, we have matter waves, or Mach number, which is basically the ratio of the velocity by the sound speed. This velocity field here. Well, there is one aspect before I end that we're going to look to the turbulence as a matter wave aspect. So this is the normal condensate expanding. This is the turbulent one. And I don't know if you are familiar with speckle field in optics. We have a laser field. We introduce a lot of disorder. This creates a speckle field, which is a random distribution of complex fields, amplitude and phase, random distributed. And I claim that this is exactly what we have in a turbulent BEC. Is a speckle matter wave. And then what I've been doing recently is characterize the turbulent cloud in expansion, not confined, as a speckle matter wave field. And of course, to do that, there are a lot of statistics in light field. So we use this knowledge on speckle, which is a statistic in the light field, to introduce here in the matter waves. And we are able, that is something very interesting, because in coherent laser field, the divergence of a beam depends on the wavelength and the waist, the size. But if you have a speckle, depends on the wavelength and the correlation length. That's why the speckle field of light expands completely different from a coherent beam. Exactly happens in our case. So we made all the correlation studies to show that they are completely equivalent. I have to jump to this. This is the correlation, right? And we measure the correlations to show that atomic cloud and light beam are exactly equivalent. This is light beam. This is the turbulent. This is the coherent laser beam. And this is the condensate, and this is the turbulent condensate. Okay, so once we have done this, we conclude many things, and especially that we are below the Rayleigh range of expansion, so we can see the domains expand, and that's why it keeps the self-similar expansion. I think this is a demonstration of merging quantum turbulence with statistical atom optics, which may be a new field. I think Gustavo will speak about the giant, the high charge vortices, and I have no time to speak about granulation, but this is a very exciting stuff, which may be related to superconductors. If we excite enough, we see grains, domains of superfluidity, and I think what's happening is we introduce so much phasing here, the system, the macroscopic system cannot hold anymore, and then creates these islands of superfluidity, and in my mind is like equivalent to short-range superconductivity when you put a lot of impurities and everything in those high TC superconductors. And we've been characterized this, and this to be explained, it goes beyond the mean field. We have to go to real many-body multi-orbital calculation, and this is being done, and incredible how the things will agree. And I jump to the conclusion, and if you are interested about the turbulence in those systems, we published about a year ago, less than a year ago, but a whole review in physics report, which has all the work we have done. At that moment, now we have to complement with some other things, but everything is somehow contained in this review paper. Thank you very much.